Welcome to today's DeepSense Discovery Session. We're going to be talking about a Smart Buoy project. But before we begin, we're going to quickly just go over DeepSense and what DeepSense is. So DeepSense is an organization that was created by all of these partners that you see on the screen. They got together and realized there's a great need in the ocean sector to pool resources together to allow companies to start looking at machine learning and artificial intelligence to better use their data. So we have some great partners through ACOA, the province of Nova Scotia, the Ocean Frontier Institute, COVE, which is the Center for Ocean Ventures and Entrepreneurship based in Dartmouth, Nova Scotia, IBM, and Dalhousie University. What we do at DeepSense is we work with academic researchers and ocean-related companies, and we complete projects, very specific projects that are focused on artificial intelligence, machine learning, and visualizations. What we found is a lot of organizations have some barriers when they try to use their data a little more effectively or in a different way. Those barriers can be that they can't really find the right use case for their data. It may be that there's some skills and expertise that they're currently lacking, or if they do have that expertise, the capacity isn't always there, they're focused on other things. Or maybe there's no access to software, some of the infrastructure that's required to do the heavy computational processing required for machine learning and AI. At DeepSense, we bring forward the types of resources that you might need to help guide and make some decisions around AI and machine learning. We work with students and we pair postdocs and undergrads and masters and PhDs to help companies try to find opportunities to use their data a little differently. We also have infrastructure that we take care of and maintain ourselves that is safe and secure, that's located on premise in Halifax, that allows us to better manage the data that we use for our projects. We also have a relationship with IBM, our IBM infrastructure that we own, we operate, but we also have access to millions of dollars worth of software and support through our relationship with them, which sometimes allows people to get a chance to try new licenses they might not otherwise try. We have a process that really focuses on trying to bring together companies or organizations in the ocean sector. We partner them with academic researchers, and then we scope out projects. At DeepSense, what we try to do is make things a little bit easier. We try to help prepare some project scoping. We help define the data deliverables, the outcomes, and also support looking for funding. We pair up with those students that help work on the project and execute. And then the goal is to provide the companies with some kind of prototype, proof of concept, or even code that they can use to commercialize for their business. So maybe they're making something faster or better or more efficient, or maybe they're making a brand new technology or service or products that they didn't have before. The students then can go on and either write projects and reports, or maybe they publish a paper and a thesis about what they learned. And the goal is those ocean companies are a little more effective and more technologically advanced. And we also have some students who recognize the ocean ecosystem as a potential career opportunity. So the big goal of DeepSense is, one, we help companies become more commercial, have a proof of concept or prototype or code using AI, machine learning, and visualizations. And we develop some skills and resources for the ocean sector. So join us Mondays at 2 p.m. Check us out on Eventbrite, on Twitter, on Instagram, on our website, and you can learn more about DeepSense. Now, we're going to pass this on over to Chris, and Chris Whidden works, and he'll share his role at DeepSense, but Chris is going to talk to you about a really interesting project that we partnered with COVE, the Center for Ocean Ventures. We also partnered with the Pilotage Association, the Port of Halifax, and a number of other groups that helped us explore a way to use data in a way that currently wouldn't have been completed before, because a bunch of organizations didn't necessarily have a conduit to bring them together and try to use that data to better understand and build a prediction tool. So with that, I'll share with Chris to take over and start and explain what this project was and what our incredible student Will completed during this project.
All right, thank you, Jennifer. So should I take over sharing, or are you just going to go through the slides?
Sure, you can go ahead and share.
Okay, after you stop sharing. Thank you.
Noted.
Okay. So we actually started this presentation off with some of those same slides. Okay, here we go. So hello, everyone. I'm Chris Whidden. I'm the Algorithms and Software Specialist for DeepSense. What that means is I do a lot of different things. One thing I do is I maintain some of that infrastructure that Jennifer mentioned, particularly making sure that we have software that we need on it, or that how to install new software that projects need. Part of that is giving advice on what software, frameworks, or algorithms people should be using in their projects. And then part of that is in a supervisory role. So I have a PhD in computer science. I did a postdoc in Cancer Research Center in Seattle. And so I have a lot of experience, and you can kind of look at me as a faculty member light. So I help writing project proposals. I go on some of these initial meetings and see, are these projects feasible? What can we imagine a student doing? And then later on, and when we have identified, here's a company, here's a project, here's a student, then I find who could be the PI that was actually working on this project and loop them in. So part of the goal of DeepSense is to bring people in and to kind of shorten that gap between when you start talking to a company and when we get a project started. So today, I'm going to be talking about...
I'm really sorry, Chris. Somebody isn't muted, and I'm trying to figure out how to mute you, and I can't. So can whoever just joined, please ensure that you're muted? Thank you. Sorry, Chris.
Yep. So that's kind of what my role is. And I'm going to share with you today a project that we had a Master's of Applied Computing Science student working with COVE and people from the Pilot Authority, and working together to try to figure out, as Jennifer said, what we could do with some of this data. So the main objective of this project, as you can see on the screen now, was to develop a prototype to predict wave and wind values of something called the Smart Atlantic Buoy. So this is a floating sensor, much like the one shown on the right here, and it records a lot of different measurements. It records various values of the wave heights, the wind speeds, wind directions, and so on. The problem is that sometimes there are problems with these buoys. The buoy might go down, it might have a failure where it's not collecting data, there might be rough waves and it gets moved around. And one of the things they use this buoy for is to determine, is it safe to go on a ship? And so it's a very crucial piece of hardware that's necessary. But if the buoy isn't giving proper data or it's down for maintenance, then the question is, what do you do? So the goal of this project was to train a machine learning model to predict what values we would be getting from this specific buoy using values from another buoy located in a different place in the harbor. Now, these are very, very different locations. The Smart Atlantic Buoy, if I recall correctly, is very sheltered. You can kind of, I think, see in this picture even, there are some rocks that are blocking it, so it gets much lower waves than the other buoy that we're looking at, the Environment and Climate Change Canada buoy, which will shorten to the ECC buoy later in this project. And we also tried taking data from land stations, just related to wind speeds, and tried to see, using this extra data, will that improve our predictions? So you can see in the lower left in this figure, we started by looking at a lot of different sources of data. This Environment and Climate Change Canada buoy, a different buoy, AZMP Halifax, Shearwater Land Station, Osborne Land Station, Pier 31 Station, and several other land-based stations. And the idea is to feed values from each of these into a prediction machine learning model and determine, can we predict the values at the Smart Atlantic Buoy for wave and wind speeds? As I was trying to get at, these buoys are used to provide decision-making guidance. If the waves are too high, then people don't go on a ship that day. So they're very, very crucial. So the idea of this is, well, one thing we could do is we could put in an additional buoy in the harbor, but that is going to be extra cost. And if we can replace that with a prediction model, then why not? Or suppose we have two buoys, that's a great redundancy, but sometimes maybe both are going to go down for one reason or the other. So it's still a good thing to test out. Can we predict values at one buoy using information from another or other station values? There were a lot of challenges with this project. So we went in thinking it would be quite simple. We had data coming in constantly from one buoy. We have data coming in constantly from the other buoy. We'll just take that data. We assumed it's going to be clean and nice, that we're going to have the same kinds of temperature and wave height and wind speed values in each of these, and we'll just throw in a machine learning model and we'll be done. It did not turn out to be anywhere near that easy. And part of the point of these discovery sessions is to share, what does a DeepSense project look like? Well, we're finding that a DeepSense project often looks like we get some data and we spend months trying to understand this data, figure out, what is wrong with this data, where are we having gaps, how can we clean this data, and so on. So in this project, actually really only the last month or so was spent doing machine learning, visualizations, and predictions. Most of this 4-month project, the first 3 months or so, was just getting access to the data, determining what data do we have, and figuring out how can we clean and align that data. So there was no data dictionary or definition of what we had with these buoys. You actually look at these and it turns out that they're recording at different times, they're recording in different ways, and it was a challenge to figure out just what can we actually predict and how to line these up. Now, you look at these buoys and they have web pages to get the data from, but they're not actually that automated, and they have different kinds of ways to access these. There were different web pages, and for one of these, if I recall correctly, we could access data 1 week at a time. For the other, it was 1 month at a time. So you had to actually go in, manually say, get this chunk of data, this chunk of data, this chunk of data, and so on. So it was not very nice and automated. And then I'll share of the next few slides problems with this data, but in general, there was a lot of mess and problems in this data. It was not clean, it was not aligned, and we were originally going to try using 4 or 5 different buoys, and we weren't able to. We ended up just looking at the Environment Canada buoy, the Smart Atlantic buoy, and a few land-based stations. Okay. So one really big challenge that took us a while to figure out what to do with is that these buoys are not collecting data at the same time. So we have some examples of what the data looks like on the left here. And on the right, we show lining up the data collection times in red. So for the Smart Atlantic buoy, we are collecting once every, I believe it's 20 minutes, once every 20 minutes. And then for the Environment Canada buoy, it was once an hour. But we do not have data collection at the exact same times. And that is a challenge for doing machine learning. But what you can also see is that one thing we could do is just say, let's cut out some of the data and just take the data that was collected at the same times. But they're not aligned. So we might collect data at, say, what's this, about 15:25, so 3:25 in the afternoon. And on the other buoy, it was around 3:20. So we aren't in control of these buoys. They're not collecting data at the same times, and they're not collecting data at the same frequency. So what we ended up having to do was some averaging. We averaged over 1 hour and 3 hour periods in order to get a constant base for prediction of these values. And so the other thing I want to say is you can see just what this data kind of looks like. So for the Smart Atlantic buoy, we have values like, here's the station, the time we were collecting data at, its location using GPS, the average wind speed, the maximum wind speed over that 30-minute periods. It's 20 or 30. In this case, 30. That 3-minute period, and the average direction of the wind. Then on the ECCC buoy, the Environment Canada buoy, the data does not look the same. So we don't have time in UTC, we have a date. We don't have the station name, we have a station ID. We have this Q flag, I don't recall what that one was. We have latitude and longitude, and it's recorded with a different number of significant digits and with a different title. We have depth, we have values that are roughly equivalent, this velocity, wind height, and so on. That wasn't it, but velocity of the wind and so on. So we have 2 different buoys, and it was a lot of work just to figure out which of these columns actually match up. So we have a problem of lining up the data, figuring out which of these are essentially the same data, and then figuring out how to average these values. So the student Will spent, I'd say at least the first month, just solving this challenge. So we get that sorted out. We're averaging, we figured out, talking to an expert, which of these values correspond to which ones are recorded in different ways and therefore not suitable for machine learning, and so on. So great, we have nice clean data, we'll throw it into a machine learning model and we'll be done by supper. No. So we have other challenges. As I said, we tried looking at about 4 or 5 different buoys, and we have challenges. I forget which buoy this was. It might have even been the Environment Canada buoy, where around sometime in 2016, the buoy actually was taken down for maintenance, and it was returned to a different location later in 2019. So you can see in red dots on the right, it was closer to the coast of Nova Scotia, and it was moved out further after that, and then now they're collecting data at that location. So even just having data from one buoy doesn't mean that that data is comparable over time. You really need to go for a deep dive into the data to see how consistent is this data and what happened with that. And so if we're going to try to train a prediction model, obviously we can't train it during that time period where there was no data collection. And also we're going to have challenges if we're going to try to train it on data that was collected in one location versus another. You really have to kind of treat it as a different buoy after the data's been moved. And you have to think ahead and wonder, if I train this machine learning model, now what's going to break? If I'm assuming it's at a given location and that buoy is moved later on, then we're going to have to try to do some retraining or other methods to be able to predict values, because it's going to learn based on the location how does the wave and wind change as it moves from that location to the location we're trying to predict. So, that's just a challenge, but we can get around that by narrowing our focus to dates that are proper or only using buoys that are more reliable. So we did that. But then even looking at our most reliable data collection, we're still going to have time periods where the buoy is not collecting accurate data. On the left, there are just going to be sometimes time gaps. So you need to really think about this when you're training a machine learning model. If it learns that, as a simple case, going from one buoy to the other, that the wave height is half the value at the other. That's of course way too simplistic, but this gives you an idea. So suppose we had 10-meter waves, and then at their location we have 5-meter waves. So that's a very simple kind of prediction. If now all of a sudden you give it a value of 0 because there is no recorded data, or worse, it's a null value or something, you're going to get garbage for your prediction. And then if someone's looking at this prediction to say, should I go out onto this boat? Is it safe? That's a problem. So you need to build error handling into your models. And then suppose that you're looking at your average wind speed, and again, for a simplistic case, it learns that the wind speed is, say, 90%. So your wind speed is 50 kilometers an hour, and then it's 4 kilometers an hour on average at the other location. Then you give it a value of minus 120, here's meters, minus 120 meters per second. What is it going to do with this garbage value? So you have to sanitize and check your inputs and make sure that when there's an error in your data, you're not going to then have an error in your prediction. So after all of these challenges are addressed and we build in sane error handling, we narrow down our buoys so that we're looking at the proper ones that are most robust for testing out that this is going to work, then there's still a lot of work. So we've cleaned our data, we've decided what we have. Now you need to take those data. Remember, they were recorded at different time periods. We put these into different months. We had to merge the files. We had to process these columns. Recall again that in both of these buoys, they had completely different naming conventions for the data. So we had to merge those. We had to handle these invalid values. We then binned the data 3 hourly and hourly, as I said before, with this averaging. We processed these individual data sets to line them up when we had data at the right times. We had to define, as I said, these data types for different columns, create calculated fields from the other columns. These are the ones we're going to predict. And we'll also divide this data into quarterly periods, essentially seasons, because the Pilot Authority, who is interested in this data, really cares most about winter. That's when they see the highest waves. And so we want to be able to check how well is this data handling in different quarters. So that's using the analysis at the end of this project. So after all said and done, as I said, this took the first 2-3 months of this 4-month project. And then Will was looking at various different ways to do this prediction. So once we've narrowed this down to consistent, clean data that's lined up, now we have what's called a we have what's called a regression problem. And we can use many different methods of doing this kind of regression to predict what the values are at one buoy using the values from the other buoy. So we had 2 essentially challenges that we focused on: predicting the wave heights and predicting the wind speeds. So we ended up going with 3 models that perform the best: support vector machines, random forests, and a very, very simple linear neural network. Now, if you're familiar with machine learning at all, you would be wondering, what about using deep learning models or other fancy models? Well, as I said, we didn't really have time to get to that. And as I'll talk about later on, that's something we want to look to in a follow-up. But here we just use kind of the two best non-deep learning models, and then a very, very simple neural network to see how it performed. We also saw there were differences between using the hourly and 3-hourly average data. And partly that's because it's easier to predict something over a 3-hour range, and because you have more historical data as you're doing it. Looking at these values with maybe I won't go into all the details here, but actually the best performing model that we saw was using the random forest model. If you're not familiar with machine learning, essentially what this does is it builds a lot of different classification trees, where given your different columns in your data, you have a yes/no condition. So is your wind speed higher than 40 kilometers? Yes or no. Is your wind speed lower than this value, or so on? And it builds hundreds of these different classification trees, tries all of them, and then if one of these trees is followed towards the bottom, then that is fed into your prediction. So that is the kind of classifier you get with a random forest. If you remember with neural networks, that's very different, where you have a set of computer neurons where you feed in your data, you do a bunch of different kinds of operations. In this case, a very simple operation where you're just feeding in values multiplied by weights on all of your different input data through one layer into another, and that's output. And at the end, you then average these values down to a single point, and that is your predicted value. And for all these methods, over time, you give it training data. We're giving examples of, here was our value at the Environment Canada buoy, here's the value it should predict, and if it gets it wrong, then it feeds backwards into these methods and improves them. So, after all this work, we get down into the weeds where we were getting wave height predictions on average that were at most 0.2 meters apart. I think the maximum was less than 1 meter, which is still very, very good. One challenge with this data is the average isn't really what people care about. What they care about is in the worst case performance, and particularly if we're close to our threshold of, is it safe to go out or not? That's when we care about the data. So as a follow-up, one thing we like to look at is narrowing down our focus at these specific values. The problem, of course, is you have less data in the most challenging conditions. So we'll have to do something like data augmentation. If you're not familiar with that, it's the idea where you take the true data you have and then you modify it in certain ways, like multiplying by a certain value, scaling it, or stretching it out in your time periods, or averaging different values to create data that looks similar to your real data, but covers these challenging conditions. So as I said, we had on average 0.2 meters off with the random forest method for the wave heights, and the wind speeds had very, very good prediction. So a little bit more than 1 meter per second off. So now I'll give some examples of what this actually looks like. Another challenge in machine learning projects is interpreting the results. So we get a value, 0.17 meters for this hourly prediction problem. Is that good? Is that usable? So here we're showing the actual versus the predicted average wave heights. So in orange, we have the actual values, and in blue, we have the predicted values. And this is showing the data for 2 months in each of these bins. And as you can see, especially at the larger values, we predict very, very closely. Sometimes it's a little bit off, but at the lower end, then we get quite a bit of variation. So this is actually, for the purpose of the Pelletage Authority, really, really good results. We're seeing that we are tracking these worst cases, and we're close enough in the other cases that we get an idea of what the conditions are. So remember what we're actually looking at here. We're saying that we have a sensor buoy that is at the edge of the harbor. We have another one that's sheltered, and we're training a machine learning algorithm to predict, based on the values at one, what we're getting at the other. So to my mind, these are really great results, showing that this is a feasible thing to do, which is what we were going for. And then, as you can see here in the next set of figures, which are the same kind of values, but for the wind speed prediction, that the wind speed prediction is tracking very, very closely to the actual values. Part of this is going back to what I said at the beginning, that we were using that one buoy to predict for the other. We were also using land-based stations. And those land-based stations don't have good don't have wave height values, but they do have wind speed predictions. So leveraging additional information is a great way to improve your machine learning models. So I kind of alluded to some of these, but the next steps for this project are to predict other wave and wind columns. We focused on, I believe, the significant wind and wave heights, which itself is already a measure that's being averaged over the 30 or hour-long periods. So what if we want to try to predict what is the actual wave and wind values? Can we see good data, for example, when we have a huge hurricane? We want to try more advanced algorithms. As I said, a lot of this project was really just getting the data, aligning the data, and cleaning the data. So there wasn't much time to look at fancier methods and to try a lot of different parameters and improve the methods that we did use. The other part is this, like many of our DeepSense projects to start, was just an example, a proof of concept showing that this project is feasible. This is research and people hadn't done this before. There's a lot of work in the literature showing, what if we have a sensor array with hundreds of different buoys and we know some of these are going to fail? Can we predict their values? So that's an established problem. But on this small scale, where you have only one or a handful of buoys, there wasn't much work in the literature. So we weren't even sure this would work at all. And we were very excited to see that it did work, and quite well, in fact. But this isn't a finished product that they can now actually use. We had all those manual steps. We had to collect data from a web page manually and clean this data. So a future project that we'd like to do would be to automate this, take data that is constantly fed in from the web, feed it into our model, predict values, and then cross-reference that with the actual values later on, use this to improve our training or to report when we're having problems. For example, if we saw that our buoy we're predicting from had suddenly moved, we want to be able to catch that right away, not days later. So, this is kind of typical for projects. You start out showing what's feasible, you improve it, and then you turn it into something that's usable. And those are very different skills that we might need to do these. We could explore doing monthly predictions, classifying waves by their direction, and looking at other things in here. And as I said, the automating the data collection piece is a really huge and crucial part of this. It's not just a matter of, here's our data, we can assume it's nicely cleaned, and we can apply machine learning. A lot of the work, especially when you're working in the ocean sector or with small companies, is in cleaning, filtering, and looking at that data. So finally, I just want to thank the Center for Ocean Ventures and Entrepreneurship, which funded this along with my tax, and everyone who's involved in this project, particularly my coworkers at DeepSense, and everyone who was involved. And we're actively looking forward to bringing this project forward. Again, actually doing these, trying out different models and trying to make this usable so that people have a stopgap if one of these important buoys goes down. Thank you very much, and I'd be happy to take questions. We ask that you post your questions into the chat, just so that we don't have a lot of people talking over each other.
Amazing. And thank you very much. I think one of the big things is a huge shout out to Will, who was our student. And
yes.
So going back, I'll come back to some questions in a second, but one of the questions is more how does this project happen? And so at DeepSense, our job is to build relationships with companies in the ocean sector to try to figure out how we can help them solve some problems. And sometimes some companies or organizations might know they have data, but might not know what they can do with it, or might have a problem, but might not know how data could solve it. And I think the big thing about this one was the buoy is used, and it's used every day by a group of people, and what would happen if it went down. So trying to figure out what they could possibly do with it was a great experience for Will. And Will was a Master's of Applied Computer Science student at Dalhousie and had to do a 4-month internship. And so his internship project was looking at this and solving this problem. And I think one good experience that anyone has anytime they work with data is, there was a question or a note in the comments talking about data governance. Absolutely, organizations need data governance without a doubt. But the thing that's interesting, Will first had to find out what data was even out there. And so sometimes in different sectors in the world, people don't always have it. Like if you look at date, like unless you're following certain ISO standards, you have varying date structures and time structures that can get collected in data. So Will first had to find the data that was available, had to source it, had to clean it. There were all of these crazy challenges that he went through. So data governance is critical. And once you have control over your data, without a doubt, continue to follow through with it. One of the questions that we have here, Chris, though, was how did you filter out the noise from the data that you can see in the graph? And how did you work with missing values?
So part of this was just choosing which buoys we could use. So when we had this kind of data, we just had to ignore it. We had to line up our time periods to the ones that we had good data, and we had to ignore some buoys that we thought we were going to include in the analysis. One thing we wanted to do was test, I think we had 3 buoys we were interested in. If we have 3 versus any individual one of these buoys, which is going to give us better prediction power? Do we need to have data from just one? Or do we need really to get good prediction data from all 3? The problem is that the data really wasn't actually usable for a long enough time period for us from the other buoys. So part of this is just picking and choosing what data sets you're going to focus on. And especially at the proof of concept stage, you want to pick the best data you can, and then maybe later on try to solve the challenges of using the other data. The other part was really just Will going through this data, trying to process it, and then failing. So, and then he would look in, see why isn't this working, and looking at the data and seeing things like these negative values. And this was a manual process, and he just wrote in rules that when he was collecting this data, he would filter out these values or set them to a sane default. So there was no nice automated way of filtering this. It was all ad hoc and done by Will. Not sure if that answers the question completely, but in some different areas, depending on what kind of sensors you have, there are nice algorithms you can use to filter the data. In other cases, it needs to be done manually. In this case, it was all manual rules that were written. Another thing you can do that I'll just add is when you're training your machine learning models, you want to make sure that if your data is going to have noise, that you train and test on cases that have that noise. So you can do things like a method called dropout, where you randomly ignore parts of either your data or some of your layers in your neural networks. And that will train the model so that it doesn't always assume it has perfect data. We did not get to that kind of stage with this data. So for the year, it was all just manual work trying to filter these.
Great. And there's a question, Chris, that is, what kind of skills would you need to do a project like this? Do you need to be a data scientist or have a high level understanding of machine learning and programming?
So you need to have a basic understanding of working with data. So being able to load up data in a spreadsheet program like Excel and look at some of the values. You better write some basic computer code, but really all of the machine learning parts we can help with. So that's part of the idea of DeepSense. In this case, it was a Master of Applied Computing Science student. He had done some coursework where he had used some of these models like things like random forest and so on, but he hadn't actually done much with neural networks. So he had a basic level of programming, a general idea of how to use Python, which is kind of the most common language for machine learning, but not the only one. And from there, it was a lot of learning and reading and looking at example projects. We did a lot of things like looking at online tutorials where people had done similar kinds of regression. Another thing about this problem is it's not actually a typical deep learning problem. And that's probably why random forest worked better than the simple neural network we tried. If you've heard about things like computer vision tasks, there neural networks are obviously the best thing to do. For prediction, there are not really good neural networks yet. So that's, again, one thing we'd want to try to look at in the future, but prediction itself is actually not as well suited to the current types of neural networks that are out. So it's a lot of just trial and error, looking at simple tutorials, and none of the steps in this kind of a basic project were really difficult by themselves. It's just that there was a lot of work to clean the data and then figuring out what is the next feasible step. So I hope that answered your question.
I think it's great. I think one other thing that we, if you think back, we had a great chat last week with Matt Zamola, Real Data, and we were talking about the skills of people that he looks for when he hires. And he talked about kind of people who can kind of figure things out, right? There was something along the lines of people, he was saying the people that he worked with kind of took on things that just tried things. And I think that was a big thing about Will's perceptions and attitudes and desire to figure things out. He didn't, there was no one for him to go and say, where do I find this data? He had to talk to a bunch of different people and brainstorm and get feedback. And it was an ongoing learning process. It wasn't like someone said, here's our data dictionary, here's the data structure, go find the data and go use something with it. There was a lot of seeking things out on his own, which turns into a lot of projects, especially if there isn't someone in an organization who's doing any kind of data science at a deep level today, or they're looking for something net new and incremental. Okay, so Chris, next question. For the large time period where the buoy was under repair, did you try time series to forecast the values to see how additional data may affect the model? If not, do you think that large amount of data, the large amount of missing time period would negatively affect the model too much?
So definitely that large amount of missing data would negatively affect the model. So sorry if it wasn't clear, but that was from a different buoy we were going to use, and we ended up not using that one. So it was just a challenge of figuring out which buoys were lining up with what we wanted to predict and which were usable. So in the future, something to do might be to try to take that data and see during the times that we did have data from that buoy, how well does it work? And the challenge there again is both it was out of the water for a very long time period, and when it went back, it wasn't in the same location. So we weren't even sure how comparable the data would be in those two different locations. So that was something we wanted to get to, but did not have time to actually look at in this project. Again, we spent most of the time for this pilot just processing the data, not really trying out different ways to analyze the data.
Got it. And how did you design the data pipeline and funnels to merge the data set from ECC to the other one?
So again, this was a lot of manual work. Will did this mostly by himself, so I don't remember all the details, but he manually, for using the web page, is again 2 different web pages for each of these data points, manually got the data in the month or week chunks. He put all this into a single CSV file, and then he filtered this himself. So he looked through it manually using Excel, and then he wrote some simple scripts that would exclude parts of this data. But it's not an automated pipeline. It gives us this nice data set that we could test some things out on, but it's not going to now take net new data and automatically analyze that net new data. So that's something we want to look into in the future.
Yes, for sure. And so Bill Cunningham has his great point. So one thing he says, it's not a big deal to have a liaise with the project subject matter expert. Fair, except we did have some issues where Will was looking at data, and Chris maybe have more context, but he didn't know, because he wasn't a subject matter expert in oceanographic type data or climate or like bathymetry, different types of any kind of data related to the oceans himself. He's focused on being a data scientist and machine learning expert. He didn't know what outliers were. So sometimes we talked about if all of a sudden there's a negative wind value, hey, a negative wind value is not logical. But if you see a lot of 5s and 7s of value, and all of a sudden you see 100, is that 100 a miss? Is that a data error? And so like your wave height, maybe you see a 5 or 10 meter, but if you see a 100 meter wave, is that considered an issue? And so there were times that we had to have some good subject matter expertise in our data and loop in with them to make sure there was some logic to the data that Will was trying.
Yeah, and to add to that, one challenge with this project is that there were quite a few different people involved, and really the people that Will most frequently interacted with weren't the people using the buoy data themselves. So we had a couple of meetings with the College Authority, but then the subject matter experts that Will was working with, it would be, oh, I don't know to answer that question. I'll have to get it back to you. And another challenge when you're working, especially in the ocean sector, but probably in many other sectors as well, you're working with a company and people that don't know enough about data. So we had a lot of questions about what can your machine learning do? And we had to try to get across that it can take a lot of different data sources automatically, but then you have to really hammer out what your goal is. And so focusing on predicting just the significant wave height and significant wind speed, getting that across to them was actually a big challenge. So, and as Jennifer said, worrying about things like outliers and so on, they did not anticipate any of these challenges when we were first scoping out this project. We actually let Will interact with him for a few weeks. We thought everything was going great. And then I had a meeting to check on his progress, and they had him creating all these charts, doing all these correlation studies. And then he understood what he had done. But then when he went to explain it to them, they would spend their whole meeting talking about what does it mean if we have a slightly higher correlation between this column and so on. And it wasn't moving the project forward. So after that, then we started meeting weekly and making sure we were focusing on what can we do, narrowing the scope down, You always have to avoid scope creep, these kind of things. And, figuring out what can we finish off in this project so that we can show some interesting results. And so there's always a lot of different things you can do. You can always look at adding in one more source of data, or can I solve this challenge of this thing, or can I optimize this method just a little bit more. And when you're working with a project that has a specific set of deliverables you want to get and an end limit, especially when you're working with companies as opposed to a regular academic project, you really need to focus on what is it I'm going to be doing and what is feasible in this small amount of time I have. So I'll try to answer all these questions, but some of them are going to be, we didn't have time to do that, but it's something we'd like to do.
Absolutely. And I think I'm just looking at some of the comments, and there's some good comments about organizations are only just beginning to realize the value of the proprietary data. Without a doubt, and we see that with so many organizations that we deal with. And I think it's one of the big things too is the complementary external data. So there was another question too about the raw data for this project. It's absolutely open to the public. And so that was one of the things though, was finding the data and finding the sources, because there are organizations like COOS, IOOS. We have a presentation with them the last Monday in April to talk about how they're bringing together ocean data. And while DeepSense is focused on ocean, other industries would face the same kind of thing. Finding data can sometimes go to many different websites, different organizations, sending emails, trying to download data. Maybe they allow you to download daily, weekly, monthly, yearly, but all at different frequencies and different formats. COOS is trying to bring some of that together, but that was some of the challenges, finding some of that public open data. Maybe you have your internal data at a company and you want to bring third-party data or external data, public data in. So finding it can be tricky. There's also a comment talking about how sometimes projects begin with the stakeholders requesting proof of a theory rather than open-ended discovery. And absolutely, I think for this one, we are very fortunate. We had great partners with the Pilotage Authority, with COVE, with the Port of Halifax, being really engaged with looking to see what we could find. But to Chris's point, sometimes when we get used to talking about data, we forget other people aren't used to always talking about data, right, Chris? So sometimes we had to level set and forget that we're so excited or know exactly what we want. Trying to articulate that can be a challenge too.
Right. And in the case where you have a student who's doing this work, he was really excited, motivated for this project, but that also means he was more willing to, go down dead ends and try out new things that if we had scoped it out a bit more clearly at the beginning, maybe he wouldn't have to spend time doing that. So it's one thing we're mindful of in the future, making sure that we narrow our scope as much as possible.
I'm just looking to see if we have any other questions out there. It doesn't look like it right now, but this will be posted online. We have a YouTube site. Please check out as well all of our other chats and join us for other chats in the future. Sorry, when chat messages come up, I realize I can't talk and read at the same time. So if you're interested in reaching out to us to learn how your organization can try to explore a DeepSense project, if you're a student who's interested, if you're a faculty member or a staff of an academic institution who's interested, really we offer the infrastructure, support with software, support with students, and try to move things along so everyone has the opportunity to really explore their data. But thank you very much for joining us. Chris, did you have anything else you wanted to add?
No, I think that covers everything.
Well, thanks very much. And please check us out online, and we look forward to you guys joining us next time. Thank you, Chris.
Thanks, everyone.
Bye.